All right, welcome. And now let's jump right in and let's talk about combining probabilities. So we've spent time talking about what a probability is, to set up the definitions, vocabulary, and we talked about how to calculate probabilities from the definitions, right? The two definitions of probabilities that we discussed before, the classical definition, right, or the theoretical definition, and then the other definition is the empirical definition, or what we call the relative frequency definition. But now we're going to talk about combining probabilities, and this is where some of the rules will start to come in that we're going to start applying. So let's talk about this. Okay, so before we start, let's talk about independent events. We say that two events are independent if the outcome of one does not affect the probability of the outcome of the other event. Okay, so that's what we mean by independent. Now, if that's not the case, then we say that the two events or three events or however many events we're talking about are dependent. Okay, now if two independent events, if we have two dependent, if we have two independent events, A and B, okay, and they have individual probabilities, P of A and P of B, then what we do is if they're connected by an and statement, so if we want the probability of A and B, and those two events are independent, then all we do is multiply their individual probabilities together. That is what we call the simplified multiplication rule. Okay, but that only we can only use it if the events are independent, and this can be applied to more than two events. Okay. All right. Okay, so let's look at an example here. We're going to look at three dice. It says, what is the probability of rolling 3 6s in a row with a single die? Okay, so that means we're going to roll the die 3 times. Okay, so now here's the question. We want the probability of 3 6s. How do we write that so that we can use this rule that we're talking about? So what we're saying is, what's the probability of getting 3 6s in a row? So that would be equivalent to saying, hey, what's the probability of getting a 6 on the first row? And I'll put a little subscript here for that. And a 6 on the second row, and a 6 on the third roll. Okay, so now when I write it this way, then it looks like, hey, I've got and statement. So I've got 3 events connected by and. Now the question is, are these 3 events independent of each other? And the answer is yes, because if I roll a 6 on the first roll, it doesn't have any effect on whether I get a 6 on the second or third roll, right? So rolls of a die are independent of each other, okay? So now I can use the simplified multiplication rule, and I can just write it as the probability of getting a 6 on the first roll times the probability of getting a 6 on the second roll times the probability of getting a 6 on the third roll. Now, what is the probability of getting a 6 in general on a 6-sided die? Assuming that it's fair. It's going to be 1 out of 6. So each one of these is going to be the same. It's going to be 1 out of 6, 1 out of 6, and 1 out of 6. And so what do we get? We get 1 over 6 cubed, which is, I believe, 1 over 216, if my math is right. Because 36 times 6, yeah, should be 36 times 6, which is 72 times 3, which is, yeah, 216. So, which again, we would write this as a decimal, of course. Now, what about dependent events? How do we handle dependent events? Well, with dependent events, it's a little bit more complicated. Okay, this is what we well, we have to use the definition. So we're going to talk about a couple of things. So the definition, so this is called the general multiplication rule. And the multiplication rule, the general multiplication rule, uses conditional probability. Okay, conditional probability by definition is A given B. That vertical slash, that vertical line is the symbol for given. And that is the formula or the definition of conditional probability is given by this, is probability of A and B all divided by the probability of B. In this case, whatever is after the given sign is what goes in the denominator, the probability of B. Okay, and so that's how we get the general multiplication rule, because all we do is solve the conditional probability for P of A and B. Okay, so whenever we have dependent events, we have to use the general multiplication rule, which is given here. Okay, and again, this is extended to any number of dependent events, but the more dependent events, the more complicated it looks. Okay. Now, the cool thing is in a lot of situations, we don't even need to use the conditional probability when we're dealing with conditional probability, or we just have to remember a couple of things. So we don't have to memorize this general rule. We just have to know how to apply it. Okay. So let's look at this. So let's use a jury selection. We have a 3-person jury, must be selected at random from a pool of 6 men and 6 women. So we have 12 people to choose from. It says, what is the probability of selecting an all-male jury? Okay. So how do we do this? Well, every time we pick somebody, so if we pick a man on the first selection, well, that changes the probability of getting a man on the second selection, because now we have one less man to choose from. Because once you choose somebody, they're done. They can't be chosen again. Once you're on the jury, you can't choose that person again. Okay? So in this case here, these are not going to be independent events, because every time I choose someone, it's going to change the probability of selecting the next person, because my sample size, right, the number of people in my pool is decreasing. Because on the first person, I have 12 people to choose from. As soon as I choose somebody, they're out. And that means that now I only have 11, right? I only have 11 people to choose from on the second selection. And then after the second selection, now I only have 10 people. So every time I choose somebody, the probability is changing. And so therefore, they are dependent events. So now what I'm going to do is I'm going to use the general rule and say, okay, well, if I select a male on the first one, right? So I'm selecting 3 people, right? So if I think about it this way, is okay, I'm going to, the probability that they're all male is equal to the probability that the first person that I select is a male and the second person I choose is a male and the third person I choose is a male. But since they're not independent, I have to use the general multiplication rule, which means I have to do this. So it's the probability that the first person is a male times the probability that the second person is a male, given that the first person was a male, times the probability that the third person is a male, given that the first and second people were both males. Okay, and so now what's the probability that the first person is a male? Well, that's going to be what? 6 out of 12, right? And then after, right, here's where the given part, now here's, what's the probability of the second person being a male given that I already got a male on this first draw? Well, now we just ask ourselves, how many men are left? The answer is 5. And how many people do I get to choose from now? 11. And now let's go to the last one. What's the probability that the third person is a male, given that I already got a male in the first and second selection? Well, now there's only 4 men to choose from, and now there are only 10 people to choose from out of the sample. So now, guess what? Now I take all of these fractions, all these probabilities, and multiply them together, and that will give me my answer. And of course, what we're going to want to do is simplify it by writing it as a decimal. Okay, and in this case, it's 0.091. So it's a very small probability. Okay, so 0.091 is the probability of selecting an all-male jury of 3 people. Okay. All right, now let's look at Venn diagrams to help us understand what it means to have independent events, or what we're going to call, well, let me just go into it before I don't want to let the cat out of the bag. But here we go. So we have 2 overlapping, non-overlapping circles. These are what we call disjoint circles, or mutually exclusive circles. So the example they give us is heads and tails. So if you flip a coin, right, you're either going to get heads or you're going to get tails. You can't get both. And so this is represented by the fact that we have 2 circles that represent each outcome, and they're non-overlapping. They do not intersect. So again, the words we use are disjoint or mutually exclusive. Okay. So now, if we have 2 disjoint circles, then what we can use is the fact that, what if we are interested in or statements? Okay, now we're going to turn our attention to or statements. If we have mutually exclusive events, what does that mean? It means 2 events that cannot happen at the same time. So if we have 2 mutually exclusive events and they're connected by an or statement, then we can use what we call the simplified addition rule. And we can just add their individual probabilities. And of course, as long as all of the events are mutually exclusive, we can extend this principle to any number of events. Okay, but all the events have to be mutually exclusive. All right, here's an either or question. So we have a single roll of a die. What is the probability of rolling either a 2 or a 3? Now, immediately you should see the fact that have an or statement. So whenever you see an or statement, you should immediately think, are these mutually exclusive? That's the question you want to ask yourself. Are they mutually exclusive? Can they happen at the same time? If they cannot happen at the same time, then they are mutually exclusive, and we can use the simplified addition rule. And so it's just the probability of getting a 2 plus the probability of getting a 3. And of course, each one of those is a 1/6. And so the probability is 2/6 or 1/3. And that's it. Not bad. Now, what if they are not mutually exclusive? What if they overlap? What if they do have some things in common? Okay, then we cannot use the simplified addition rule. We have to use the general addition rule. So let me look at this. Think about this as counting. Remember, in probability, basically you can boil it down to, we're just counting things, right? We're counting how many outcomes give us an event that we're interested in. right? So if we're looking at the probability of getting either a queen or a club, right? So that's what we're dealing with here, queen or a club. Well, what I can do is I can count up all of the outcomes that give me a queen, right? So that'll give me a number. That'll give me 4. And then if I count up, and then of course I want to count up all the outcomes that give me a club. And that's going to give me 13. But notice what happened in the middle. I double counted one of the cards. So that means I counted too many. So that means I have to subtract off one of the things I double counted, which was the queen of clubs. So that is how we do the general addition rule. We're going to add the probability of getting a queen. We're going to add the probability of getting a club, and then we're going to subtract off the probability of getting both a queen and a club, because that's the intersection that we have to subtract off. And so, in general, whenever we have two events that are not mutually exclusive, we add their individual probabilities, but then we subtract off the probability of getting both. Because of the double counting. Now, the cool thing is think about this. What if they are mutually exclusive? Then what is the probability of getting both? If we go back to here, what's the probability of getting a heads and a tails on a single flip of a coin? Well, what's the probability? There's no overlap. So what's the probability of them happening at the same time? 0. So if we go back to the general rule, the cool thing about the general rule is if we have two mutually exclusive events, then we know that the probability by definition is 0. The probability of them happening at the same time is 0. So this probability just goes to 0, and it just reduces to the simplified addition rule, which is kind of cool. Okay? So that's how we get the simplified addition rule. And by the way, if we go back to the multiplication rule, if we look at the probability of B given A, right? What if those two events are independent? What if A and B are independent? Then guess what? It doesn't matter whether we know A has occurred or not. The probability of B given A, if they're independent, just equals the probability of B, because it doesn't matter whether A has occurred or not. So if we understand the general multiplication rule, and we understand that if the two events are independent, then the probability of B given A just reduces to the probability of B, and we just get the simplified multiplication rule. So just something to think about. All right, so now let's go forward. All right. All right. Now let's look at an example of where we have events that are not mutually exclusive. Okay. It says, what is the probability of a standard shuffled deck of cards, a shuffled standard deck of cards, that you will draw a 5 or a spade? Okay. A 5 or a spade. Okay. Well, how many 5s are there in a deck? There are 4. How many spades are in a deck? Well, there are 13 cards of each suit. So in this case here, a spade, which is one of the suits, has 13 cards. There are 4 suits, 52 cards in a standard deck. That's one thing you may not know. Okay. And there are 4 suits. So 13 cards for each suit adds up to 52. Okay. So there are 4 5s, but there is also a 5 of spades. So these are not mutually exclusive events. Okay, so what do we have to do? We have to use the general rule. So the probability of getting a 5. Now again, this is only with or statements. So anytime you have an or statement, 5 or spade, then you ask yourself, are these two events mutually exclusive? If they are, we use the simplified addition rule. If they are not, we use the general rule. In this case, they are not. So we're going to use the general rule, which is going to be the probability of getting a 5 plus the probability of getting a spade minus the probability of getting both a 5 and a spade. And so what's the probability of getting a 5? Well, there are 4 5s out of 52 cards. So that's going to be the probability. Plus the probability of getting a spade. Well, in that case, there are 13 spades out of 52 cards. Minus the probability of getting a 5 and a spade. So there is a 5 of spades. So there's only one card that's both a 5 and a spade. And that is 1 out of 52. And so now all we have to do, since the denominators are the same, this is why I didn't simplify the first two, because the first one would have been 1/13 and the second fraction would have been 1/4. But I kept everything with 52, so it's easy to add and subtract. So all we have to do is add across the top and subtract. So in this case here, we'll end up with what? 17 minus 1, which is going to be 16 out of 52, which is going to be what? It's going to be 4/13. And of course, I would write this as a decimal. All right. Now, here is a special rule. This is for at least one. Okay. This uses what we call the complement rule. Okay. Now, in this case here, it lumps two of the rules together, and I typically don't like that. Okay. It uses the complement rule, and then it uses the fact that they're independent events. Okay, so it uses the simplified multiplication rule, okay, multiple times. Okay, so you can memorize this if you want, but in the next example, I'm going to show you how you could just use what I call the complement rule. And the complement rule is just using, especially whenever you have at least one, you want to use the complement rule. So the complement rule, if you remember, is the not, right? It's the probability of A is equal to 1 minus the probability of not A, or A prime. Okay, so instead of this, just use A prime. Okay, so now I can use the complement rule with at least one, because if you have at least one of something, the opposite of that, or the complement of that, is none, right? So I either have 1, 2, 3, or 4. So at least one means I have 1, 2, 3, or more, right? So if I want the complement of that, or what's not at least one, that would be none. I would have none. So if I use the complement rule with at least one, then I use this way. I use the probability of at least one is 1 minus the probability of none. And in a lot of cases, that is a much easier probability to calculate than to calculate the probability of at least one, because you have to consider all of the options. You have to take the probability of at least 1, or 2, or 3, or 4, or 5, all the way up to whatever. Okay, so in a lot of cases, using the complement rule is a lot easier. So let's look at an example. We want the probability of at least one head when we toss a coin 3 times. So we want the probability of at least one head. Now that means if we want to do this by brute force, we would have to calculate the probability of getting one head or getting two heads or, oops, three heads. Well, this would mean how many different ways are there of getting one heads? Well, that would mean the probability of getting H tails or H, oops, wrong one. Oh, let me back up. Oh, wrong side, hold on. Okay, so or tails, heads, tails, or tails, tails, heads, or now we're going to get two heads. So that means either or heads, tails, heads, or, and you see what I'm going, right? So we'd have to calculate a lot of different probabilities, right? Okay, so let's go back. And let's use the complement rule. And so this means this is equal to 1 minus the probability of getting no heads. Well, how do we translate this? Well, this is the same. Now we're going to use, what does no heads means? Well, this is equal to 1 minus the probability that we do not get a heads. Oops, wrong way. H, not N. So probably we don't get a head on the first flip, and we do not get ahead on the second flip, and we do not get ahead on the third flip. And now we can use independence because they're connected by and. So the first question you ask yourself is, are these independent events? And the answer is yes. And so now we can write this as a using the simplified multiplication rule. So this is just going to be the probability of not getting ahead on the first toss times the probability of not getting ahead on the second toss times the probability of not getting ahead on the third toss. Now, what is the probability of getting ahead on any flip of a coin? It's 1/2, right? So now we know that each of these probabilities is equal to 1/2. So now we just write it as 1 minus 1/2 times 1/2 times 1/2, which is equal to 1 minus what? 1/2 raised to the third power. So you didn't even need to memorize the formula. So this is equal to 1 minus 1/8, which is equal to, 7/8, which again, I would write that as a decimal point out the 3 decimal places. All right, there you go. See, we got the same answer. All right, let's look at this. You purchased 10 lottery tickets for which the probability of winning some type of prize on a single ticket is 1 out of 10. What is the probability that you will have at least one winning ticket among the 10 tickets? So you purchased 10 tickets, right? So, and you want the probability of having at least one winning ticket. So again, I would use the complement rule here. So we want to do the probability of at least one winning ticket, right? And that's going to be 1 equal to 1 minus the probability of no winning tickets. And so now this, again, we have 10 tickets. Having no winning tickets means that each and every one of the 10 tickets we have is not a winner. So the way we'd write that is 1 minus the probability that the first ticket is not a winner and the second ticket is not a winner and let's just dot, 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 and all the way to the 10th ticket is not a winner. Now, again, these are connected by and statements, so the question we ask ourselves is, are these events mutually exclusive? So if one ticket I have, one of the tickets I purchased is a winning ticket, does that affect the probability of the other 9 tickets being a winner or not? And the answer is no. So these are independent events. Each ticket is looked at as its own independent event. Okay? Whether one ticket is a winner or not doesn't affect the probability of any of the other tickets being winners. Okay? Okay. And the reason is because all the tickets are chosen at random. Okay, so I'm going to use the simplified multiplication rule. So then I'm going to write this as its individual probability. So this is going to be 1 minus, and I'm going to put brackets because we're subtracting the whole thing. So this is going to be the probability that the first ticket is not a winner times the probability that the second ticket is not a winner, and then of course times all the way to the probability of the 10th ticket not being a winner. Okay, now the question is what is the probability of any individual ticket being a winning ticket or not being a winning ticket? Well, they tell us what the probability of winning is because they say it's 1 in 10. So that means that the probability of any individual ticket being a winner is 1/10, which means by the complement rule, again, think about the complement rule, each ticket is either going to be a winning ticket or not a winning ticket. So that means the probability of not being a winning ticket is the complement, right? So not winning is the complement. So that's going to equal 1 minus the probability of winning, which is going to equal 1 minus 1/10, which is equal to 9/10. So the probability of not winning is 9/10. So now we can move forward. And so it's going to be 1 minus 1/10 times 1/10 times 1/10 times all the way to times 1/10. And we're going to do that 10 times, which means that it's going to be 1 minus, oh, not 1/10, I'm sorry, 9/10, because we're saying not winning. I'm sorry, that was my bad. Okay, and so it's going to be 1 minus 9/10 raised to the 10th power. And then, of course, you could stick that in your calculator and solve. And so the final probability, the probability of having at least one winning ticket is not too shabby. It's 0.651. So better than half, right? So not bad. All right, that's it. And if you have any questions, please reach out to me, and I'll help you in any way I can. Practice these. Probability is one of these things you need to practice. So please practice.